Yeah, the next topic is how ion selective electrodes work. The basic principle behind ion selective electrode is potentiometry. That means you measure potential change with respect to the concentration change. Okay, so there is virtually no current flows in ion selective electrodes. You simply measure a specific ions depending on their concentration. Okay, and you by measuring the potential using Nernst equation, you know the concentration of the ion of your interest. Okay, so now let's take a look at how ion selective electrodes work. ISE in short responds selectively, okay, to one specific ion. For example, liquid-based ion selective electrode um, is the example. Okay, uh, here actually this electrochemical setup is very simple. You have a reference electrode, and then you now you prepare this ion selective electrode. And ion selective electrode inside in it there is a internal reference electrode. So you measure the potential difference between internal and external reference electrodes. And internal reference electrode, its role is to measure the potential developed by this ion selective membrane. So the essential part in ion selective electrodes is this ion selective membrane. Okay, so this membrane plays an important role. This membrane, as the name indicates, it will respond to a specific ion. For the purpose, this membrane should be impregnated with uh, ion 4. Okay, here ion 4 that binds a specific ion. Okay, and depending on the ion concentration change in the, between internal solution and analyzed solution. Okay, as you know, the potential develops between the membrane when the concentrations, two concentrations are different. Okay, do you understand? So if you want to measure a specific ion, for example, ion A in a light solution, and also you have to have that ion inside this ion selective electrode. Okay, and you have to prepare this membrane impregnated with ion 4. Yeah? Okay, so let's blow up this part. Yeah, yeah, this is membrane. Okay, uh, and this part is filling solution. That's the internal solution. Okay, internal reference solution, and this is the external solution. And this is the ion selective membrane. Okay, and ion selective membrane contains ion 4, like this one. In this case, it is represented uh, as L. Okay, now you have analyzed solution outside the electrode, and here you have cations and anions. Okay, and you want to measure this the concentration of this cation. Okay, so you have to have the same cation in the internal solution. Okay, the filling solution here. Okay, yeah. Okay, although the anion is different, cation is the same. Okay, and then let's consider what happens inside this ion selective membrane. Okay, now here, since this ion selective membrane contains ion 4, yeah, ion 4 as the name indicates, the ion 4, a specific ion 4 bind specific ions. Okay, now L here uh, suppose you may see the R minus one. Yeah, R minus one is the anion. Uh, you see the actually the ion selective membrane composition. Uh, it contains several ions, okay, or several kind of components, okay. But essential part is that it contains ionophore. In this case, valinomycin. Yeah, this is the forensic structure of valinomycin. Yeah? Valinomycin is antibiotics. Yeah? It is very difficult to synthesize. Okay? You have to separate this valinomycin from others. Anyway, yeah? Now you uh, yeah, impregnate this membrane with valinomycin, and it has the air molecule inside, and air now respond only to this cation, okay, here. So Lc plus, there are complexes, okay. Actually the valinomycin is specific to potassium ion, okay. Also it can bind the sodium ion, but mostly valinomycin binds to potassium ion. Anyway, now this ionophore valinomycin binds this cation, and then now it moves to here to the internal uh, inner surface of the membrane, okay. And here uh, internal the solution also has the same ion, in this case potassium ion, okay. So there will be a potential difference here, okay. The outer the membrane surface and inner membrane surface, okay. And actually the only the variable in this case is the concentration of C plus, okay. And here is in the filling solution, in the filling solution this cation concentration is constant. It is made constant, okay. So also in the in this interface, okay, internal the membrane interface, there is a potential uh, what drop. Also here is a potential. The potential is developed, okay. But only and then all these potential differences are governed by Nernst equation. Yeah, but as I said, all other the terms are constant except the, this cation concentration outside the electrode, okay, in analyzed solution, okay. And actually the measurement is simple and quick, okay. Yeah, and very easy actually, okay. Here this valinomycin makes a complex with potassium ion, okay. So potassium ion is transported across the hydrophobic cell membrane, okay. This is very important in our living cells, okay. Okay, inside the membrane complexation reaction is this one, okay. This is ionophore and cation, and this is complex, okay. Large, so this is equivalent constant is so large. The large Kf formation constant means a small amount of free L and cation in the membrane, okay. So cation can diffuse across the membrane. R minus and L they remain on in the membrane, and anion cannot enter into membrane because valinomycin, this one only respond to cations, especially potassium ion, okay. If cation diffuse from membrane into aqueous phase, excess plus charge in aqueous phase develops, okay. Here you understand, because uh, this one cation now diffuse into the inside the membrane, okay. Yeah. This imbalance creates potential difference opposing diffusion of more cation into aqueous phase. Okay, yeah. Once uh, it is complexed with air here, and then there will be a potential difference. Yeah. And that potential difference, the oppose diffusion of more cation into aqueous phase. Okay, when cation diffuse from membrane to outer solution. Okay, here the potential difference is given by this thermodynamic equation, delta G here, yeah. And then later on we can convert this equation uh, in terms of potential, since delta G is related to potential by delta G equals minus NFE. Okay, anyway, delta G equals delta G solvation, and the solvation gives free energy change, which is delta G due to change in solvent. Okay, and minus sign here, uh, well, so that sign depends on which one we take the reference. Anyway, let's take this negative sign. Yeah? Negative sign means diffusion from high to low activity. Okay, and RT log logarithm of, of the ratio of this activity coefficient. Okay, this AM is the activity of this cation in the membrane, and AO is the activity of cation in the outer solution. Okay, and what? Yeah, yeah, although this derivation is looking complicated, but final equation is really simple. At outer surface of membrane, the living driving force for diffusion of cation from membrane to outer solution is favorable solvation uh, of cation by water. Actually, the cations are solvated by water. Yeah? Build up plus charge in water. The charge separation creates outer membrane potential here across the membrane. Okay, so here we can write it this way. The solvation gives free energy change minus RT log of this ratio, and minus NFE outer membrane potential equals 0. Okay, and this part is delta. Actually, this is also delta G here. Okay, you see this is delta G is the due to charge imbalance. Okay, these two terms keeps free energy change due to transfer between phases and activity difference. Okay, so potential difference, actually we if we divide by uh, this equation NF, okay, we get this one. Outer the membrane potential difference across the outer the membrane is given by this one. Okay, and this is constant if delta G solvation is constant. Okay, and RT and F also constant, and what this part, yeah, inside the membrane cation activity is constant, and only variable is the cation concentration, okay, in the outer solution. Okay, and then if we keep doing for the inner filling solution, okay, and actually the E is the potential difference between the internal reference electrode and outer reference electrode. Okay, and we get this part. We already obtained this equation here, and minus E inner. Okay, and E equals this one. This is constant, uh, and we you know this part log and then we can expand like that, and then the membrane, the potential difference is also already all the time is constant. Okay, and this part, as I said, this AM, right, cation uh, concentration inside the membrane, is constant. Okay, it doesn't change. Yeah? This constant and only variable is the outer uh, you know, solution concentration, analyzed concentration. So it can be simplified as this one. This is final equation we arrived. E equals constant plus RT over NF logarithm A uh, 0. That is AO. Okay. So uh, this one, this equation is really important since we are mostly working under the room temperature. So the measured potential difference is E equals constant plus this part 0.05916 divided by n multiplied by logarithm of outer membrane analyte activity. Okay, yeah, this one. So and we have to define which sign is given to ions, right? For customarily, traditionally, plus sign is given to cations, okay? Because cations takes it has positive charges, okay? And negative sign is given to anions, okay? Yeah. And here is the number of electrons. So for the monovalent ion, like potassium, sodium ions, or even anions, yeah, for the ion selective electrode, chloride anion, yeah, nitrate anion, and then n equals 1, yeah, for the anti valent the ions like kappa divalent kappa ions, and what maybe barium ions, yeah, those things, or sulfate ions, and then n equals 2. Okay, very simple. Yeah. So here 59 millivolt, roughly about 60 millivolt for every factor of 10 change in activity of proton in analyte solution. Okay, if it is this one uh, is protons. Okay. Okay, so ion selective electrode, in the principle, anyway, the derivation is not simple. Actually, if you refer to the uh, you know the more what advanced book for the ion selective electrode, and then you will find more difficult equations, more complicated equations, and derivation is quite complicated. Okay, but don't worry about that. Yeah? Here's solvation energy is only treated, but not only when ion 4, or when the ions are placed in aqueous solution, there is a solvation energy, and also there is another energy is involved, which means that let's see, uh, depending, let me see. Yeah. So here the solvation energy is very important. Yeah, but when uh, the you know ion 4 changes its shape, and also there will be energy associated with it. Okay, so what I mean is that actual situation is quite complicated, yeah? And then derivation is not simple, but the final equation we arrived is very simple actually, right? So you remember this equation, all right? And conventionally, this one, the plus sign is given for cations and minus sign is given for anions. Alright, so as you know here, in ion selective electrode, yeah, that is one of the potentiometry, which means you measure this potential, okay, potential change, and then you can relate this potential to the concentration and activity, yeah, in a precise way. Okay, yeah, let's stop here temporarily.